Hello, my name is Macie Watley, and this is Lab 5, Motion of Falling Object. The main objective is to use the momentum principle to observe how gravitational force and drag force affect the position versus the time. The main result observed was the force due to gravity modeled in Python shows a curved graph, and adding in the force due to drag in the Python code, the model fits the observed objects dropping closer. Neither objects reach terminal velocity in the time recorded. Here are the videos of me dropping a purse as a heavy object and a Mr. Clean magic eraser as the light object. Right now we're looking at the light object, the eraser. I calibrated the picture frame in the back of the image in meters by measuring it with a ruler. The axes in both videos are oriented with the negative y in the direction the way that the object falls, and the positive x direction pointing in the upward direction. I did this so that the direction of the object starts falling at 0 and goes in the negative y direction. The video clip begins just as the object is released from my hand and right before the object touches the ground. The magic eraser's average location is marked in the middle of the object. The origin is located in the middle of the object at the beginning of the video clip so that it starts at 0, 0. Now let's look at the heavy object. The descriptions I just described also fit the video of the heavy object, the purse, falling as well. So the same axes pointed and oriented in the same direction for the same reason. Here's the Python model for the light object. The mass I measured to be 0.005 kilograms, and the initial position is at 0, 0, 0. And since the ball is dropped from rest, the initial velocity is 0, 0, 0. The time starts at 0 seconds and goes to 0.875. The time step is 1/24, and this was chosen because that is the interval that I marked the objects falling in tracker. Here you can see how I used the momentum principle to derive the formula V final equals V initial plus F net delta T divided by M, which is what we used in the Python to the model. The net force is a combination of drag and gravity. Derivation of the momentum principle is going to be the same for the heavy and the light objects. Initially, we're going to model accounting for force due to gravity, which is negative 9.81, and the y component. The time interval for the heavy object is 0 seconds to 0.4583, and the mass is 10 kilograms. So this is what the module looks like when it's run. And that was the light object. Drag force equals negative v times the magnitude of velocity times the unit vector of the velocity. Now to find the net force, we just add the force due to gravity to the drag force. I found the b for the light object to fit best when it equals 0.0145. So here we have the data in Python. This column is the time, here's the position, here's the Python position while we're just accounting for gravity, and here's when we account for drag. And over here you can see these modeled. So this is the light object, and this is not accounting for drag. And you can see that's a pretty good fit in the beginning, but it really veers off course in the end, predicting a different end position. But in the second one, when we accounted for the drag, you can see the fit is much closer when you from what Tracker predicted and from what the Python module predicted. So it's exactly what we wanted to see, that the two forces really can predict the motion. So here we have the heavy object. It's the same layout. Here's the time, here's the position, here's the predicted position from Python, and here's the predicted position with drag. You can see the slope is about the same here, even without drag. The good thing is that the slope is predicted to be about the same, so it's the speed is increasing with the same amount. So what does it mean? I've already added the velocity to the Excel sheet to save the time by using the position divided by the time. Here you can see that the velocity never reaches a constant for the heavy object for Tracker with or without drag. So here we have the light object with the velocity versus the time already modeled. You can see that without the drag, it's a very different model, neither of which reach terminal velocity. With the velocity versus time with the drag, the model matches closely, or more close, but it still doesn't reach a terminal velocity. It gets closer. It's only off by a couple of hundredths of a decimal place from terminal velocity. So with just a little bit more time, with the drag calculated, the light object would have reached terminal velocity. The what if question. We can model if the object were thrown down by giving it an initial velocity in the downward y direction with and without drag. I changed the velocity to be 0, negative 9.810 initially. First ran it without drag and then with drag. For sake of time, I'm not going to show you this, but I did it in Python, and then I got the results to an Excel sheet. Now we look at the data in Excel. You can calculate the velocity by doing position divided by time for each row. You can see that for both with and without drag, it never reaches terminal velocity. Here's the velocity thrown without drag, and here's with drag. And it's always changing. It never hits a constant. If we would increase time, say drop it off the top of a building instead, the object would have a higher chance of reaching a terminal velocity. Thank you for listening. I hope you enjoyed.